So friends, this is a numerical problem and this is a simply supported beam, and there are 3-point load A, C acting at C, D and E of magnitude W, 2W and 3W respectively, and we have to draw the shear force and the bending moment diagram for this problem. So the first step is the determination of the reactions at the point B and the point A. Suppose the reaction at the point B is RB and the reaction at the point A is RA, okay, acting in vertically upward direction. Now we know that reaction at A plus reaction at B is equal to net vertical load acting over this simply supported beam, and it is equal to W plus 2W plus 3W is equal to 6W. And using the equation that the summation of all the movement about this pinpoint or the hinge is equal to 0, that is movement about the point A is equal to 0, we have to find out these two reactions. So this RB is contributing toward a movement of RB into x plus x plus x plus x, that is 4x, okay, in anti-clockwise direction about this point A, and this force is causing a moment of minus 3wx into x plus x plus x, that is 3x into 3, that is 3x, that is 3w into 3x about this point A in clockwise direction, and clockwise is treated as negative. Similarly, this will account for a moment of minus 2w into 2x in clockwise, and this will account for minus w into x, this distance is clockwise, and you have to put this all thing equal to 0. Now when you solve this, you will get RB is equal to how much? 7 by 2w, okay, which will be equal to 3.5 w going in vertically upward direction. So RB is equal to 3.5 W, and RA is equal to, when you solve this, putting RB into this equation, you will find RA equal to 2.5 W going in vertically upward direction. Now friends, you have to draw the shear force diagram. Now friends, we will find out the shear force at the point A, C, D, E and B on the left side and on the right side. So we have to find out the shear force at the point A on the left side of the point A. For that, we have to construct a section on the left side of the point A, and looking on the left side of this section, you can see that there is no force acting on the left side of this section. So shear force on the left side of the point A is 0. Now shear force on the right side of the point A we have to find out. For that, we have to construct a section XX on the right side of this point A, and you can see that on the left side of this section, this force is accounting toward us positive shear force of magnitude 2.5 W. Positive sign is taken using this sign convention, okay, and on the left side of the point C, if you want to find out the shear force, then you have to construct again the section on the left side of the point C. Now looking on the left side of this section, you can see that this force is accounting toward a positive shear force of magnitude plus 2.5 W using this sign convention, positive taken, and shear force we have to find out on the right side of the point C. For that, we have to construct a section on the right side of the point C. This is the section XX constructed here on the right side of the point C, and looking on the left side of this section, this force is contributing toward a positive shear force of magnitude 2.5 W, and this is contributing toward a negative shear force of minus W using this sign convention. Negative is taken here and positive is taken here using this sign convention, okay, so it will give us 1.5 W, okay. Now we have to find out shear force on the left side of the point D. For that, we have to construct a section on the left side of the point D. This is the section XX here constructed, and looking on the left side of this section, this force is contributing toward a positive shear force of 2.5 W magnitude using this sign convention, and this force is contributing to a minus W shear force using this sign convention, and it will again come out to be minus 1.5 W. Now shear force on the right side of the point B, if we want to calculate, then we have to construct a section on the right side of the point D. Now this section XX is constructed here on the right side of the point D. Looking on the left side of this section, This force is contributing toward a positive shear force of 2.5 W using this sign convention. This is contributing toward a negative shear force of minus W using this sign convention, and this is contributing toward a shear force of minus 2W about this section XX, having minus sign using this sign convention, and it will give us a shear force of minus 0.5 W. Okay, now shear force on the left side of the point E, if you want to find out, then we have to rub this section and construct a section on the left side of the point E. Okay, on the left side of this section you can see that this force is contributing toward a positive shear force of 2.5 W. This is contributing toward a negative shear force of minus W. This is contributing toward a negative shear force of minus 2 W, and it will again give us minus 0.5 W. And shear force on the right side of the point E, if you want to calculate, then we have to again construct a section on the right side of the point E, and shear force on the left side of this section, we have to find out. This force is contributed toward 2.5 W, and this is contributing toward minus W. This is contributing toward minus 2 W. This is contributing toward minus 3 W, and all of these will give us how much? Shear force on the right side of the point E minus 3.5 W. Now shear force on the left side of the point B, want to determine, then we have to again construct a section on the left side of the point B. Okay, now this is the section constructed here. Now this force is accounting for a shear force of plus 2.5 W, and this calculation will repeat itself, minus W, minus 2 W, minus 3 W, and it will again give us minus 3.5 W. Now shear force on the right side of the point B, if we want to calculate, then we have to again construct a section on the right side of the point B like this, and looking for the various forces. This force will contribute toward 2.5 W, this will contribute toward minus W, this will contribute plus 2 W, this will contribute toward minus 3 W, and this will contribute toward this force plus 3.5 W using this sign convention. Okay, so it will give us how much? 0. So we will draw the shear force diagram now. Now see friends, at the point A shear force is 0, so making cross here, and on the right side of the point A it is going to plus 2.5 W plus 2.5 W. So above the point A 2.5 W will lie, and on the left side of the point C it is going to plus 2.5 W will lie in same level, and on the right side of the point C it is going to 1.5 W, that is it is decreasing to something here as 1.5 W. Okay, and on the left side of the point D it is going to 1.5 W, so lying in same level here 1.5 W, and on the right side of the point D it is going to minus 0.5 W, so it minus 0.5 W will lie here somewhere, minus 0.5 W, and on the left side of the point E it is going to minus 0.5 W, it will lie in same line, and on the right side of the point E it is going to minus 3.5 W, so minus 3.5 W will lie somewhere here, minus 3.5 W, and it is going to 0 on the left, it is going to minus 3.5 W on the left side of the point B, so lies here, and on the right side of the point B it is going to 0. So joining first point with the second, second with the third, third with the fourth, third with this fourth, fourth with fifth, fifth with sixth, sixth with seventh, seventh with eighth, eighth with ninth, and ninth with 10th, we will get our shear force diagram. And these lines are horizontal lines because there is no loading line between the point AC, CD, DE and EB. That's why these are horizontal lines. So this is the shear force diagram. Now we will draw the bending moment diagram. Now we will calculate the bending moment at the point A, C, D, E and B directly. We do not have to calculate on the left side of the point A and on the right side of the point A. Similarly, we have to do it for C, D, E and B. We do not have to do that. We have to directly calculate at the point A, C, D, E and B because there is no concentrated movement acting at any of these points A, C, D, E and B. So we will directly calculate the bending moment at these points. So bending moment at the point A, if you want to determine, then we have to construct a section at the point A passing through this point A. This is the section XX, and looking on the left side of this section. Now we will calculate the bending moment at the point A, C, D, E and B directly because there is no concentrated movement acting at any of the point A, C, D, E and B. That's why bending moment will not change when going from left side of the any of these point to the right side of any of these point. So we will directly calculate the bending moment at the point A, C, D, E and B, because there is no concentrated movement acting at any of these points. So bending moment at the point A, if you want to find out, then we have to construct a section here at the point A, passing through the point A, and looking on the left side of this section, there is no force line, no concentrated movement line. That's why bending moment at the point A is 0. Now bending moment at the point C, if you want to find out, then we have to construct a section here passing through this point C. Now looking on the left side of this section, this force will contribute toward a bending moment of magnitude RA, which is equal to 2.5, that is 2.5 W into this distance x. Using this sign convention, it is treated as positive. Okay, this sign convention. Now bending moment at the point D, if you want to calculate, then we have to construct a section passing through this point D, and looking on the left side of this section, this force will contribute toward a bending moment of 2.5 W into 2x, that is x plus x is equal to 2x, creating a positive movement, bending moment using this sign convention, and this force is causing a bending moment of minus W into this distance x, causing a negative bending moment using this sign convention. So it will give us the bending moment value as 4wx. Now bending moment at the point E, if you want to find out, then we have to again construct a section passing through this point E. This is the section XX, and you can see that on the left side of this section, this force will contribute toward a bending moment of 2.5 W into this distance x plus x plus x, that is 3x. This force will contribute toward a bending moment of minus W into this distance x plus x, that is 2x. And negative sign is because of this sign convention, and this force will contribute toward a bending moment of minus 2W into this distance x, and negative sign because of this sign convention. Okay, so it will give us the value of bending moment at the point E. So this will come out to be 3.5 Wx, and bending moment at the point B can be find out by constructing a section here at the point B. Then you can see that bending moment at the point B can be find out using constructing this section. Now looking on the left side of the section or on the right side of the section, you can find out the bending moment at this section XX. We have earlier looked on the left side always to find out all these things, but now I am looking on the right side of this section. You can do it on looking on the right side of the section. On the right side of the section, there is no force line, no concentrated movement line. That's why bending moment on the right side of the section is 0. That's why bending moment at the point is 0. You can do it by looking on the left side and calculating the effect of all these forces for the bending moment of this section X. You will find the same answer as 0. So now we will draw the bending moment diagram. So the bending moment diagram will look like this. Here at the point A, the bending moment is 0. It is going to 2.5 Wx here at the point C, and it is going to 4wx at the point D. This is 4wx at the point D, lie somewhere here, and it is going to 3.5wx at the point E, and it is going to 0 again at the point B. Now the line between point A and C is the bending moment between point A and C is joined with a inclined line, because the shear force diagram is a horizontal line between the point A and C. Similar is true for all these lines, because shear force diagram is straight line between points C and D, D and E, and E and B. That's why these three lines are inclined lines. So this was all for today's topic, friend. If you like my video, you can subscribe my channel. Also press the bell icon for the notification of the upcoming videos. Thank you, friends.